Hello, my name is Kristopher Bedka, and I'm a research scientist at the NASA Langley Research Center in Hampton, Virginia. I'm going to talk to you today about an exciting project I've been working on for a few years called Hailstorm Risk Assessment using Space-Borne remote sensing observations and reanalyses. I'd like to credit my partners on this project from NASA Marshall Space Flight Center in Huntsville, Alabama, and also colleagues from Science Systems and Applications Incorporated in Hampton, Virginia. So why are we studying hail here? Well, hail is the costliest severe weather hazard for the insurance industry, generating conservatively about tens of billions in losses across the world due to damage to homes, businesses, agriculture, and infrastructure. I say conservatively because we really don't know where all of the hail events around the world have occurred and what the losses from those are. But you can see on the left just some sample tweets I captured at various times as I've been perusing social media. And for example, the upper left, you can see that hail can accumulate so deeply that it could prevent cars from traveling through roads. This is an event that occurred in Argentina. In the lower left, you see a field of peas that was completely decimated by a hailstorm in Alberta. In the upper right, a pilot from Zambia went through a storm, and the hailstones completely ablated all of the paint off the nose cone and damaged the metal airframe of the aircraft, which must have been a very scary flight to be on. In the lower right, you can see an example of just how large some hailstones can get. These are up to 11 centimeter hailstones in Slovenia, but hail can get much larger. Hail can get to be approaching 20 centimeters large. I believe there was an event in the United States where such large hail was observed. And so in order to estimate risk from hail, insurers use hail catastrophe models or CAT models. And so CAT models are developed with climatologies that define hailstorm frequency and severity. But these climatologies are really difficult to derive over developing nations, especially that don't have robust hail reporting networks and infrastructure or climate quality weather radar observations. So that's why I said initially that we really don't know how great the damage is across the world due to hail, due to the lack of reporting. But in order to mitigate this and help development of CAT models, we can look at satellite imagery. And so satellites have been observing the Earth now for about 60 years, actually, just about. But we've really had really high quality data that can be useful for studying hailstorms and the detailed processes within them for about 25 years or so. And so hailstorms generate unique patterns in this satellite data, and this offers a new opportunity to identify hail-prone regions. So in this project, we're trying to push the satellite data to the limit and really get at how well can we perform climatological hailstorm analysis that can enable CAT model development and hailstorm resilience around the globe. Also, through the products that we developed with automated detection of severe storms and hailstorms, we can improve their understanding and warning in regions without adequate weather radar coverage. We also analyze hailstorm damage signatures after the storm has come through in high-resolution optical imagers like Landsat or VIIRS or MODIS or Sentinel-2, or synthetic aperture radar data that can see through clouds and look at damage patterns on the land surface to assess opportunities for post-disaster mapping and response. And if you want to learn more about all the details of this project, there's a link at the bottom of this page that you can go to and read about it. And so really want to talk about how we do this climatological hail study and mapping of hailstorms throughout history. Well, first of all, we're going to do a little bit of an anatomy of a hailstorm. And so what you're looking at here in the middle is a photograph from an aircraft of a hailstorm producing hail about 5 centimeters in diameter right at the time of this photograph. And you see a rapidly rising air column that is producing a bubble in the cloud top. And that bubble you can actually start to see some of that bubbling occurring in this animation that I just started from the GOES-16 satellite that collected images every minute of a severe hailstorm that impacted Burke-Burnett, Texas. You see the bubbling, and so these bubbles are very cold, they're very textured, and we can develop automated pattern recognition techniques to identify those overshooting cloud top updrafts that we call them that are serving to generate the hailstones in the storm. We also have lightning observations from space that we can also use to study the electrical activity and identify storms that are the most likely to generate hail based upon their lightning flash rates. Also, from passive microwave imagers, the Earth is always emitting energy in microwave wavelengths as well as in the infrared. But as the microwave energy comes through with wavelengths of, say, a millimeter or a fraction of a centimeter, it hits, in a hailstorm, it hits a bunch of hailstones that are much larger than the wavelength of the radiation. And so therefore that radiation does not make it to the satellite sensor, which results in a clear signature of a hailstorm in this passive microwave imager data. So we have the visible, the infrared, lightning, passive microwave are the primary data sources going into this project. And so we can take this data and aggregate it over long time periods. Here I'm showing data over South Africa throughout the day. So I used our pattern recognition algorithms to identify convective anvils in the magenta contour. And then we also drill deeper and look at the details within those anvils to try to identify those overshooting tops and characterize them in terms of their temperature, their area, their overall penetration through the surrounding anvil, and all of this. We take that data and combine it with the passive microwave climatology that we generated from TRIM and GPM, my colleagues at NASA Marshall Space Flight Center. And so we aggregating all of these passive microwave signals together and identifying those hailstorms. You can see that there's clear hail hotspots that occur throughout the world. In some places, you're exceeding 5 hail days per year. So you have over the central U.S., Colombia, southeastern South America, like Argentina, southern Brazil, Paraguay, and Uruguay, tropical Africa, the Mediterranean and South Africa regions also are kind of moderate hail hotspots. And then you get to Pakistan and Bangladesh and parts of Australia that also have a fairly high hail frequency. And data that made this map is available at NASA at the link here. And so you take this passive microwave data that we use to identify the environments around hailstorms, so wind shear, instability, other parameters, and combine it with the geostationary infrared-based overshooting cloud top detections and find overshooting tops that are in very hail-prone environments, and then take that data and process it in sophisticated ways to develop a CAT model. And so you see data that we've produced here at NASA Langley. We shared it with Karlsruhe Institute of Technology and Willis Re and Willis Towers Watson, now owned by A.J. Gallagher, and use that data to define where in South Africa hailstorms are most common. And you see that the red shading in the lower right, or on the eastern side of South Africa, that's where we have the highest hail likelihood across the nation. And so moving on to the damage mapping component of the project. So here you're looking at several different satellite sensors. So the top one is a synthetic aperture radar RGB decomposition image from Sentinel-1. And so with the way we combine several different polarizations and channels here, you can see the damage to the land surface from a derecho storm, so a very strong windstorm that generated winds in excess of 140 miles per hour near Cedar Rapids, Iowa, but a huge swath of wind damage and also wind-driven hail damage throughout the state. And you can see the damage due to the crops laying down as and basically changing orientation from the SAR data. Whereas if you look at the MODIS Terra True Color image, you don't really see a notable browning across most of the area that we identified with the SAR data. And that's because the crops are just laying down and not necessarily are dead yet. So the SAR data helps you to see details that the true color imagery doesn't necessarily show you. But when you really zoom in, say to over a particular town like Breda, Iowa, which was impacted by some of this wind-driven hail, you can see basically the complete scouring of the land surface there, where you have the brown color just to the east of Breda, Iowa, and there's a photograph to the right showing what the corn looked like within that particular field. So as you really drill down, the details start to appear that maybe weren't quite so apparent in the coarser spatial resolution MODIS data. So we're really trying to take this data, push it to the limits in terms of damage mapping, but also using this data to generate CAT models, providing products and software tools by the end of this project to aid severe weather and aviation weather forecasting, and also using our data, putting it into ArcGIS-based tools that are web-based to be able to have anyone in the community visualize and also access the data sets that the climatological data sets that we're generating in this project. So thank you very much for your attention. My name is Kristopher Bedka from NASA Langley Research Center, and I look forward to collaborating with all of you. Thank you.